Controlling the bionic arm to certain gestures using ROS serial communications. Abstract. The project aims to provide an aid which will help the physically disabled ones to enhance and upgrade their human capabilities. Those people with disabilities face discrimination and barriers that restrict them from participating in society on an equal basis with others every day. The work is to develop a robotic arm that provides sufficient mechanical support with better accuracy within affordable cost. The system has sought to simulate the natural movements of the arm and hand. Since this project is beneficial to the paralyzed patients, it is socially important in many cases. Researches are done on automatic prosthetic using different methods. The main disadvantages of these methods were its structural complexity and high manufacturing cost. Keywords: robotics and automation, bionic arm, robotic operating system, ROS serial communication. Introduction. The project aims to develop an exoskeleton robotic suit. How? Hybrid assistive limb. One will help people with disabilities to do their daily needs without any external help. Persons with disabilities face discrimination and barriers that restrict them from participating in society on an equal basis with others every day. They are denied their rights to be included in the general school system, to be employed, to live independently in the community, to move freely, to participate in sport and cultural activities, to enjoy social protection, etc. A person with physical disability is not able to execute activities associated with movement, both the persons himself and objects. Such immobility resulting from disorder of the muscular or skeletal system may include disability resulting from injury or disease. Technology is a valuable tool that can be used to improve the lives of people with disabilities. In recent years, the number of amputation patients continues to rise due to disease, traffic accidents, etc. Cosmetic devices developed for amputated persons have no active functionality, they provide only passive support, which will restrict the free movement of human body. 2. Methodology. A. Design a human-like bionic arm. The conceptual design is brought into virtual platform with the aid of SolidWorks. The required joints and parts are assembled and finger mechanism has been done according to the desired hypothesis. B. Safety analysis, prototyping, and testing. Safety analysis and optimization is performed using simulation platforms such as ROS, robotic operating systems. Technical drawings are prepared. Assembling and prototyping is performed in Fab Lab. User testing of prototype is performed and necessary modifications are done in iterative manner. 3. CAD modeling and hardware. Fabrication. The CAD system is built from the GUI interface, graphical user interface, which is interacting with the IJERT data, boundary representation, or geometry using the geometric modeling kernel. It may also be employed to manage the associated relationships between the geometry and sketch or a component in an assembly. A. Models. B. 3D printing the hardware. The arm is 3D printed as per the required CAD model. Printer details, FDM fused deposition method. Material used, PLA. Tensile yield strength, D638 psi. Tensile modulus, D638 psi. Melting point, D3418 degrees C. Glass transition temperature, D3418 degrees C. C. Electrical design and control parameters. Arduino Uno comes with USB interface. The USB port is added on the board to develop serial communication with the computer. It is an open source platform where anyone can modify and optimize the board based on the number of instructions and tasks they want to achieve. This board comes with a built-in regulation feature which keeps the voltage under control when the device is connected to the external device. Reset pin is added in the board that reset the whole board and takes the running program in the initial stage. This pin is useful when board hangs up in the middle of the running program. Pushing this pin will clear everything up in the program and starts the program right from the beginning. Operating voltage, 5 volts. Input voltage, 7 to 20 volts. A servomotor 27 is a rotary actuator or linear actuator that allows for precise control of angular or linear position, velocity, and acceleration. It consists of a suitable motor coupled to a sensor for position feedback. It also requires a relatively sophisticated controller, often a dedicated module designed specifically for use with servomotors. They are not a specific class of motor, although the term servomotor is often used to refer to a motor suitable for use in a closed-loop control system. Servomotors are generally used as a high-performance alternative to the stepper motor. Using standard logic level signal to control, we'll be able to drive a 2-phase stepper motor or 4-phase stepper motor, and 2-phase DC motors. Adopt a high-capacity filter capacitor and a freewheeling diode that protects devices in the circuit from being damaged by the reverse current of an inductive load, enhancing reliability. The module can utilize the built-in volt tube 78M05 to obtain 5V from the power supply. But to protect the chip of the 78M05 from damage, when the drive voltage is greater than 12V, an external 5V logic supply should be used. Drive voltage, 535V, logic voltage, 5V and PCB size. 4.2x 4.2 cm. For simulation using ROS. The Robot Operating System, ROS, is a flexible framework for writing robot software. It is a collection of tools, libraries, and conventions that aim to simplify the task of creating complex and robust robot behavior across a wide variety of robotic platforms. ROS was built from the ground up to encourage collaborative robotic software development. For example, one laboratory might have experts in mapping indoor environments, and could contribute a world-class system for producing maps. Another group might have experts at using maps to navigate, and yet another group might have discovered a computer vision approach that works well for recognizing small objects in clutter. ROS was designed specifically for groups like these to collaborate and build upon each other's work, as is described throughout this site. A ROS robotic operating system. Developing a robot with a computer brain requires a bunch of software tools on the computer side like software drivers, third-party tools for computer vision and simulation tools. ROS framework gathers all these tools and manages to develop a code for robot. It's a special framework initially developed by the Stanford AI Laboratory in 2007 for developing robots. The Open Source Robotics Foundation now maintains ROS. The concept of ROS goes far beyond just a framework. ROS is an OS in concept because it provides all the services that any other OS does, like hardware abstraction, low-level device control, implementation of commonly used functionality, message passing between processes, and package management. It is possible to integrate ROS with real-time code. Even though ROS is still a framework that isn't a standalone OS or an RTOS and isn't the only framework for robots. B steps for archiving robot position control using ROS. The URDF, Unified Robotic Description Format, should be generated on SolidWorks named as ARM, preferred. First open a new terminal on ROS either by searching terminal on search bar or by pressing Ctrl plus Alt plus T at same time, and one or more tab can be opened on same terminal by pressing Ctrl plus Shift plus T. Robot URDF is the basic key element for simulation on ROS and which is to be moved onto a workspace. Named CatCanWS, using the code CD CatCanWS on terminal or by normal copy-paste method in SRC on CatCanWS. Then should generate a moveit package. Releasing the MoveIt package by ROS launch MoveIt setup assistant.launch. A new MoveIt package window is opened. Click on Create New MoveIt. Configuration package. Browse then from the desired location the package Robot 1 is selected from which URDF is loaded on the MoveIt package. If the robot model is successfully loaded, robot model appears on window. Next self-collision matrix needs to be generated. It checks for each link pair and categorizes the links as always in collision, never in collision, default in collision, adjacent links disabled, and sometimes in collision, and it disables the pair of links which makes any kind of collision. Virtual joint need not to specify on here, hence it is for mobile robots. Planning group is a group of joints/links in a robotic arm which plans together in order to achieve a goal position of a link or the end effector. Two planning groups are to be created, one for the arm and one for the gripper. Since end effector is not used, only one planning group is created. Planning group window appears. In this window group name is given. Next is the selection of the kinematic solver. From the drop-down box select kinematics plugin. The arm group kinematic chain is added. For adding different poses for robot, click on the robot poses, and same in case for adding robot pose, where fixed poses like the 0 position and home position in the robot configuration are added. That's where we include our desired hand gestures. The last step is to generate configuration files. Click on the Browse button to locate a folder where configuration file that is generated by the Setup Assistant tool has to be saved. After browsing the required folder, click on the Generate Package button. This will save the files into the chosen folder. Then exit Setup Assistant, which will exit us from the tool. See motion planning of robotic arm in Arvis. Arvis allows to create new planning scenes where robot works, generate motion plans, add new objects, visualize the planning output, and can directly interact with the visualized robot. MoveIt. Package includes configuration files and launch files to start motion planning in Arvis. Next step is visualization of the robot. For that demo launch file is launched. The command is ROS launch rpp MoveIt demo.launch. Arvis window is opened which consists of several tabs. On Context tab from OMPL drop-down list select RRT. Next is Planning tab where the start state, goal state, plan a path, and execute the path of the robot can be assigned. Plan button is used to plan the path from the start to the goal state, and if the planning is successful, path can be executed by using Plan and Execute button. Robotic arm simulation using Gazebo. Gazebo is a multi-robot simulator for complex indoor and outdoor robotic simulation. We can simulate complex robots, robot sensors, and a variety of 3D objects. The simulation model for a robotic arm by updating the existing robot description can be created by adding simulation parameters. To launch the existing simulation model, add world.launch and bring-up.launch files needs to be added to MoveIt. Package. Now open a new terminal to launch Gazebo using the code ROS launch rpp MoveIt arm world. Arvis is used to control the robot on Gazebo, which creates a robotic environment similar to the real world. The controller can be called using the command ROS launch rpp MoveIt arm bring up. After running this command, both the Gazebo and Arvis windows are opened together and the motion path planned on the Arvis is achieved on the Gazebo. When the actual robot is fabricated, the Gazebo is released by the robot and the robot can be controlled by using Arvis. After completing all the above steps, the robot can achieve the desired poses. The hardware interface. The finger mechanism is controlled using servo motors. There are 5 servo motors. A servo shield is used with the Arduino Uno to perform the finger actions accordingly. Data is output from a sensor via a controller and interface pair. Just as a physical model may use a controller and interface to receive control commands, a sensor can use the controller and interface to process sensor data and publish it to libgazebo. Sensors do not have a physical representation. Instead they define how data is captured from the Gazebo environment. Result in conclusion. The main objective of this thesis is to develop a robotic arm that assists the arm amputees to perform certain hand gestures. The goal to design and develop an artificial limb having sufficient grasping strength, response speed, and a visual appeal in an open-source platform is achieved. The components required for the robot is manufactured by using laser cutting and 3D printing technologies. Finally, a 5DOF robot is manufactured to achieve the objectives. A control system has to be developed for the motion of the robot. It includes obtaining the coordinates and joint angles of the target position. The trajectory planning can be done using softwares by interfacing the robot with ROS. Hardware interface using ROS and Arduino is done using ROS serial communication.